All right, so I believe this is where we had left off in our previous class meeting. We were using Laplace domain circuit analysis techniques or S domain circuit analysis techniques to see whether or not we were going to wind up getting the same result as our time domain work for a second order transient analysis problem like we had seen previously in circuits 2. So we found out what the roots are. What I'm going to do now is I am going to divide the numerator and the denominator by 10 so that I can get things as, s squared and all of that kind of stuff so that I don't have to worry about thinking about the math here. So 10 divided by 10 is obviously 10. And then 10 s squared divided by 10 is going to be s squared. 2s divided by 10 is going to be 0.2s, and 10 divided by 10 is just plus 1. So I could rewrite this thing, v of s, as some unknown coefficient b1, which will be a complex number, divided by, actually, hold on, let me change this. 10 times, or excuse me, 10 divided by s plus 1/10 plus j 3 square root of 11 over 10 times s plus 1/10 minus j 3 square root of 11 over 10. And this can be partial fraction expansioned, yes, I'm using it as a verb, into some coefficient b1 over s plus 1/10 plus j 3 square root of 11 over 10 plus b1 conjugate divided by s plus 1/10 minus j 3 square root of 11 over 10. All right, so how do we find b1 for this thing? Yes. So these values of these roots, I think this is the third time that I've answered this question, so everyone please pay attention. These roots need to make these things go to 0. So if I have a negative 0.1 here, I need a positive 0.1 here. I hope that's the last time I have to answer that question. How do I find B1? By s plus 1 plus. Okay. So s plus 1/10 plus j 3 square root of 11 over 10 times v of s. So that's just going to be 10 over s plus 1/10 plus j 3 square root of 11 over 10 times s plus 1/10 minus j 3 square root of 11 over 10, evaluated at s is equal to negative 1/10 minus j 3 square root of 11 over 10. Brody, I believe you were the one answering correctly, so thank you for that. So if I throw this into my calculator, what I wound up getting was, let me find it here, 5.025 and some change, just rounding, with an angle of 90 degrees. Obviously, B1 conjugate is just this same number, angle negative 90 degrees. So from here, I actually should be good enough to go ahead and jump straight into the time domain. So what's my answer going to look like in the time domain, right? V of t in the time domain. Which identity am I going to use? On our sheet, it looked like number 15 or something like that, right? So I'm going to multiply this magnitude by 2. So that's going to give me 10.05 and some change. I'm going to have e to the negative 1/10. So e to the negative 0.1. Cosine omega is 3 square root of 11 over 10. Plus my phase angle of 90 degrees. Now, u of t. Now, in this form, it doesn't quite match what we got previously. Right? So if I scrolled up here a page, we got it as a sine function. But how do we convert cosine to sine? Subtract 90 degrees. So the exact same results as we got using our time domain analysis, we got using our S domain analysis. Okay. Where this thing right here, once again, we could call this sine 3 square root of 11 over 10. All right, so let's look at something a little more rigorous. Let's say that I have the following circuit. I have some time domain current. I'll define it in a moment. And over here, I have a 1 kilo ohm resistor. Over here, I have a 1 kilo ohm resistor. Here, I have a 2 millifarad capacitor. And I'm trying to find my capacitor voltage as a function of time if IS of t is 5u to the minus t plus 5e to the negative 3t u of t milliamps. So effectively, because I have something going on for negative values of t, I'm going to have an initial condition on my system that we're going to have to take into account in our S domain analysis. Right? So for t is less than, let's call it 0 minus, our circuit is at DC steady state because 5u of negative t is just 5 milliamps constant value. Here's a 1 kilo ohm resistor. Here's a 1 kilo ohm resistor. My capacitor is going to look like an open circuit. And since I'm trying to find the initial conditions on this, I'm going to label this capacitor voltage VC of 0 minus. What should this be? I'm hearing 5 volts and I'm hearing 0. One of them is correct. 5 volts is correct, right? So there's no voltage drop across the 1 kilo ohm resistor. So whatever voltage drop occurs across this 1 kilo ohm resistor is the same as the capacitor voltage. 5 milliamps times 1 kilo ohm is 5 volts. We all okay with that extraordinarily rudimentary circuit analysis? Okay. All right. Now let's look at what's going on for t greater than 0 plus. We are going to be looking at things in the S domain, right? So for t greater than or equal to 0 plus, we're going to have some current. I'm just going to call this IS as a function of S in the S domain, and we'll figure out what that is in a moment. Here's my 1 kilo ohm resistor. Here's my second 1 kilo ohm resistor. Here's my capacitor. And since my capacitors, it has a initial condition on it, I need to include something, right? So I could choose to do this with a capacitor in parallel with a current source or a capacitor in series with a voltage source. I'm going to choose to do a capacitor in series with a voltage source. Okay. Where this voltage will be the initial condition, so 5 volts divided by S. The impedance of my capacitor is 1 over SC, so 1 over 2.5 times 10 to the minus 3 is going to look like, excuse me, 2 times 10 to the minus 3 is going to look like 500 over S in the S domain. So I have 500 over S ohms here. And I'm going to put some terminals out here just so we can remember what it is that we're actually looking for. So before we start rocking and rolling, what is the Laplace transform of my source current going to look like for t greater than 0 plus? 5 times 10 to the minus 3 over S plus 3, right? Because we're in milliamps. So 5 times 10 to the minus 3 over S plus 3 amps. All right. So how do we want to solve this? I can think of a couple of different ways, but I'd like you guys to take a stab at things, and I'll tell you if I don't want to do this. So KVL, what the only known voltage drop we have in the whole system is this 5 volts over S right here. So to do KVL anywhere else, we wind up having to need to know currents flowing through all this other stuff. So that could be a part of things. Gavin. Source transformation. Source transformation. I had not considered that. That's actually probably easier than the way that I was doing it, which means this problem is going to take less time and we're going to get out of here early, but sure, it seems legit. What I can't believe I didn't even think about that. What I had wound up doing effectively was mesh, where this is a known current so that you go through it. But source transformation is probably easier, so let's do that. Okay. So a source transformation on this thing, we are going to have five over S plus 3 volts in series with, I'm just going to put this 1K in series with this other 1K, so it's going to look like 2K. $500 over S ohms plus or minus 5 volts over S. And once again, this is our VC as a function of S that we are looking for, and then we'll go back into the time domain to solve it for V of t, or VC of t. Okay. That made things significantly easier. I still feel like a real jackass for not noticing that, but it is what it is. So from here, what would we do? So I'm gonna say no to voltage division for, well, the most obvious reason is because this VC of S that we're trying to solve for includes the voltage drop over this source. So that's gonna make things a smidge wonky for voltage division. Not saying it couldn't be done. I would argue, hopefully you guys would agree with this, that the voltage drop across the 500 over S ohm capacitor plus this 5 volts over S is going to be DC. The easiest way to find the voltage drop across this guy would be to find the current, and we could find the current simply by doing KVL around that loop, or really just kind of Ohm's law, right? So let's say that, let's see, our total voltage is going to be 5 over S plus 3 minus 5 over S, where these things together have units of volts, must be equal to some current. Let's just call it I as a function of S, and let me label it on our diagram. Times 2000 plus 500 over S, where this thing has units of ohms. So once we solve for whatever I of S is, it'll be very easy for us to figure out what the voltage drop across that capacitor is, okay? So from here, using just good old simple algebra, we would have 5 over S plus 3 minus 5 over S, all in volts, divided by 2000 plus 500 over S, all in ohms. So it's very obvious that this is going to wind up giving us a current. How can we pretty this thing up? Because right now it's a weird ratio of the sum of things, and that's odd, and I don't like it. Okay, so we could multiply by S over S to get rid of some things. And then I'm also going to multiply this guy right here by S plus 3 over S plus 3. Okay. So in my numerator, that's going to look like 5S minus 5 times S plus 3 divided by S plus 3. Once again, this thing has units of volts. I'm sorry, what?
The S. Yeah, the S. So you multiply the top by S, it multiply like 5S, so the 5 over S plus 3, multiply by S, it multiply the top.
Why would I? I'm going to multiply this denominator by S as well in a moment.
Where did the S go? The 5S, like when you add it, you have.
So when I multiply this top part by S by itself, I'm going to have 5S over S plus 3 minus 5. Right?
Okay, yeah.
Then I'm multiplying this 5 by S plus 3 over S plus 3 so that I have a common denominator. Now I need to multiply this thing by S, which is going to give me 2000S plus 500 units of ohms. Okay. So what does 5S minus 5S plus 3 look like? Negative 15 over S plus 3. where the units of this thing is amps. Are we okay with this? Anybody got beef with my algebra? I'm bad at it, so it's okay if you do, but I think this is correct. Okay. So now what I'm going to do, now that I have this thing, I'm going to say that VC of S is I of S times 500 over S ohms plus 5 over S volts. That's effectively just Kirchhoff's voltage law around this right-hand path. So negative 15 amps divided by S plus 3 times 2000 S plus 500. Multiply this by 500 over S. Have units of ohms there, so this is a voltage. Plus 5 over S volts. Are we okay to this point where I'm literally just doing substitution of things? All right, so now to make my life easier, I'm going to factor this 500 out here, which means I'm just going to divide this thing by 500 so that it's less ugly, right? So that's going to look like negative 15 volts, where I'm taking amps times ohms to give me volts, divided by S times S plus 3 times S plus, this is going to be 4S plus 1 plus 5 over S volts. We okay with that? So 500 here is going to cancel out, so it's going to leave 4 here and 1 here. Is that okay? Pretty sure that's how math works. All right. And so let's see what else I can do. I know that having this 4S here is going to be problematic. So I'm going to divide this 15 over 4 to get rid of this thing. Right? So that's going to look like negative. So let's see, 15 over 4 would be 7.5 over 2, so 3.75. Divided by S times S plus 3 times, excuse me, S plus 1/4. Where this thing is in volts, plus 5 times S plus 1/4 times S plus 3 divided by S times S plus 1/4 times S plus 3, so that I have a common denominator so that I can lump everything into a single expression. And so that is going to give me 5 times S plus 1/4 times S plus 3 minus 3.75 divided by S times S plus 1/4 times S plus 3. With the units of this thing, once again, being volts, so that we're clear of what quantity we're working. So this is something that I can use partial fraction expansion to find the inverse Laplace transform of Brody and Jacob.
Could you just not expand what's in the bracket? That it's volts over that. Or the negative 3.75 volts. Could you just not expand that instead of dividing plus 5s? Because you're just gonna expand. That's where I was gonna do. Because you do a loss of the negative 3.75 over s plus 3, s plus 1/4, and then do a loss of
5 over s.
Laplace over s.
Yeah, but I mean, if I'm gonna have to do this part anyway, why not do it in one go? You're saying do the Laplace at the left-hand side, then do the Laplace at the right-hand side and add them together. I'm saying lump it all together and do the inverse Laplace transform once.
You can expand what's in the brackets and then do the inverse Laplace.
Yes.
Okay.
Yeah, so I could do a partial fraction expansion of this. And then a partial fraction expansion of this, and then add those results together. But that is one more step than just doing the partial fraction expansion of this, so I'm just gonna do this one. Right, so I'm not gonna add, what you're suggesting would require me to add things together in the time domain, and I don't wanna do it. I just wanna have something in the S domain that I can get the inverse Laplace transform of. If you want to do it the way that you're suggesting, I have no beef with that whatsoever. I'm just trying to get something where I have a numerator in S and then something that I can partial fraction expansion in S on the bottom. And so I'm in that state. You're correct. You could do it that way. I'm lazy and don't want to. All right. So what case is this? What do we have? Distinct real roots, right? So we're going to have V of S or VC of S will be of the form A1 over S plus A2 over S plus 1/4 plus A3 over S plus 3. How do we find A1? Multiply that thing by S, evaluate it at 0. Right? So A1 is going to be 5 times S plus 1/4 over S plus 3 divided by S plus 1/4 over S plus 3. This bit cancels this bit cancels this bit. We evaluate this at S is equal to 0, and we get 5. Right. Oh, yep. Sorry, I missed that 3.75 thing. Thank you for that. Minus 3.7. Oh, and now those things can't cancel, so I'm just bad at math today. All right. So I have to actually do this. Damn. S is equal to 0. So 5 times 1/4 times 3 minus 3.75 divided by 1/4 times 3 is something I need a calculator to do. Well, what did you guys get? I got 0 as well. So let's think about whether or not that makes any sense here, right? So the inverse Laplace transform of this term was going to be something multiplied by a unit step function. We have first order RC circuit where we're taking a source away and then inputting an exponentially decaying function. So would we really expect a unit step function to be part of that response? Probably not. Seems reasonable. For A2, we are going to have 5 times s plus 1/4 s plus 3 minus 3.75 divided by s times s plus 3. All of this is evaluated at s is equal to negative 1/4. Give me a moment to throw that in my calculator. Actually, so the numerator is just going to be negative 3.75 because we're going to cancel that part out. So negative 3.75 divided by negative 1/4 times, let's see, so negative 2.75. You're right, it is positive. Yep, 3 minus 1/4 is positive 2.75. Again, just real bad at math today. All right, so 3.5 divided by 0.25 times 2.75, 5.4545. So that's something divided by 9. So let me multiply this by 9. Oh, nope. Okay. I hear whispering and tittering. What's up? What mistake did I make? Okay. Yep, 60/11, 5.45 repeating. Okay. Yep. Yes.
So for H is multiplying our function from s plus 1/4.
Yes.
So should that s plus 1/4?
The s plus 1/4.
Oh, it's already in there.
Yeah, so it's being multiplied by this whole thing, and then this bit is going to cancel that bit, which is why we just have the s and the s plus 3 on the bottom left over. So I'm skipping a step where I'm officially canceling stuff out like we have been doing in the past, but I believe this is correct. All right. And then for A3, we're going to have 5 times s plus 1/4 times s plus 3 minus 3.75 divided by s times s plus 1/4 evaluated at s is equal to negative 3. Right. So once again, we're going to have negative 3.75 because that whole first part of the numerator is going to go away when s is equal to negative 3, divided by negative 3 times, now this is going to be negative 2.75. My mental math is correct, which it has not been today for many, many things. All right, so negative 3.75 divided by negative 3 times negative 2.75. So negative 0.45 repeating, so that would be negative 5/11 maybe. Yeah. Pause. We good? Okay. So from here, BC of T is going to be 60 over 11 e to the negative 1/4 t minus 5 over 11 e to the negative 3t u of t. And Gavin, darn you for making this problem take 20 minutes less than I thought it was going to take so that we get out of here. Oh, no. All right, so what I have on the agenda for Monday is looking at problems that actually require nodal and mesh analysis. And I want to make sure that MathCAD is going to work the way I think it's going to work when we have systems of these and we're trying to figure out how all that's going to shake out. Because doing all of that kind of substitution by hand is going to be, I think you guys would consider it a hate crime. I'm going to try to figure out how to bend MathCAD to my will and show you how that'll shake out to make your life less of a pain in the ass. So anyway, all right, I'm done for the day.